Welcome to another video in which I show you something that I haven't figured out so that to see if any of you can help me. And the topic of today, it's an expression that comes out when I am looking at the geometrical structure of classical mechanics in the relativistic setting. There is some kind of tensor-like expression that comes out and I haven't been able to figure out exactly what it is geometrically, and I've asked a bunch of people that work on general relativity and they haven't been able to tell me, so maybe one of you can help me. It's kind of interesting though, this thing, because what we're doing is sort of seeing how much of relativity, of general relativity, there is already inside particle mechanics without doing field theory. So let's get started. I have some notes here that are already written, so we're just going to go through them so that I can tell you what the problem is and I don't have to write all the math, so that is actually nice and typed and you can understand what it is. So the expression that I'm interested in is this one here. I call it G alpha beta gamma, and it's basically, this is the metric tensor in both cases, and what we are taking are derivative on the first index anti-symmetrized. And as we will see, this expression comes out by doing a simple calculation, and it should kind of feel it should be some type of inertial force tensor, but I have no idea. So let me give you a little bit of more detail of what is it that I'm trying to do, and maybe we can make this a little bit bigger without putting it underneath my face. There you go. So just to give you some notation, we have this is the exterior product, the wedge product, and it's basically the tensor product anti-symmetrized. And so if we have a tensor that it's contracted with a E alpha wedge E beta, and by E alpha these are going to be the bases, in this case the covariant bases. And what happens here is that we can expand this with this expression, and you basically get this tensor either with E alpha tensor E beta and minus E beta tensor E alpha. And then what you do is that you can switch around these two, right? And by switching around these two, you're also going to have to switch around these two. And then what you basically see is that this expression is essentially equal to one with the tensor product instead of the wedge product, and an anti-symmetrization of the tensor. So, okay. Then these are just things for myself to recall how the properties of some of the properties of the metric tensor, and these are just for me to remember how you get the Christoffel symbols with this. Of course, if you haven't done Riemannian geometry or general relativity, this is completely going to be gibberish. I'm not going to be able to tell you what these things are, but you can go and look online for other resources. So now the point is that this is all stuff that one does in Riemannian geometry, at least these two elements and the metric tensor. And what I'm going to show you is that actually the metric tensor appears in what is it called the symplectic geometry, which is the geometry that one uses in classical mechanics for classical Hamiltonian mechanics. And in fact, what we're going to see is that the metric tensor is part of the symplectic form, which essentially work like some type of metric tensor, but it's anti-symmetric instead of symmetric as the metric tensor. So, okay, let's go a little bit slower and show you what are the basic elements for symplectic geometry. So in symplectic geometry, you have something called the symplectic form, which is typically written as an omega. And this essentially characterizes the geometrical space of position and momentum, of phase space. And so this is the identity in n dimensions. So if you had a single particle, this would be 3-dimension and 3-dimension, and therefore you are in the 6-dimensional space of position and momentum. And typically these are going to be for the position components of omega, and these are the position momentum components of omega, and so on. And you can see that basically it's kind of like an identity matrix rotated 90 degrees between the position and momentum. And what this thing is actually doing, the geometric information that you get are essentially the areas on position and momentum. So you can think of the symplectic form as essentially counting the configuration for each independent degree of freedom. And so you would have essentially something that it's can be written as a dq dp, in the same way that you would write typically the line element in Riemannian geometry or in relativity. You would write it like this: dq alpha g alpha beta dq beta. Well, dx, yeah? Let's use what you usually use, x alpha, and this would be dx beta. So this would be essentially the square of the length of the line element. And in symplectic geometry you have something similar, which you typically write as something like dq alpha, in this case dp alpha. And you can imagine this as essentially becoming something like dxc a omega ab dxc b. Okay, and this is essentially, instead of being a line element, it's essentially an element of the surface, and it tells you the area of the surface in terms of numeric configuration. And this is basically the geometry that one uses to do statistical mechanics, to compute the entropy inside volumes of space and so on. So that's more or less how it works at high level, but for our perspective is just a matrix, and it's actually a tensor, but a tensor in phase space, so not just in position, but in position and momentum. And this can be understood as what is called the exterior derivative of this other canonical one form. And you can kind of see that these are the spatial component, and these are the momentum component. The momentum component are 0, and the spatial component is actually the form momentum. So sort of that's why the form momentum is important geometrically, because it's essentially the vector potential for the symplectic form. So it tells you it's a potential for the number of configurations. And so you take this vector here, and you make what is called an exterior derivative, which is basically the derivative where we are using this anti-symmetrized tensor product. And if you do the calculation, you get exactly this symplectic form, which is the thing that we use to calculate areas in phase space. Okay, so this is sort of the general idea, and then from the symplectic form you can get to the Poisson brackets, you can get to the Hamilton's law. They can all be written in terms of the symplectic form. Okay, so what we're going to do here is that typically these things are written in position and momentum, because position and momentum are canonical variables. They're special because they sort of allow you to write the canonical, the symplectic form in this very, very simple way, in this 0, 0 identity minus identity. And that's why position and momentum are the good coordinates to calculate areas in phase space and volumes in phase space if you're doing statistical mechanics. But there is nothing preventing us to actually use a different set of coordinates. And so the first thing that we're going to do here if this allows us to do it. I don't understand. Okay, there you go. Is we can use, instead of conjugate momentum, we can use kinetic momentum, which is essentially m g alpha beta u alpha. So we were basically going to calculate mv, where actually the velocity is expressed as in let's see, contravariant, covariant components. Okay, and so what we are going to do is essentially take the Hamiltonian for a particle in under electric and magnetic field, and it turns out that if you have this expression here, the momentum turns out to be mg alpha beta u beta plus q, where the q is the charge and a alpha is the vector potential of the electromagnetic field. And the Hamiltonian actually turns out to be simply one half over m of the norm of the kinetic momentum. So the Hamiltonian is basically purely kinetic. Even if you are in terms, if you have forces, still the energy of the system in this expression of the Hamiltonian is just the kinetic part. And I have to warn you, this is not your typical Hamiltonian. This is sometimes called the Hamiltonian constraint. It's kind of the proper way to do Hamiltonian mechanics in the extended phase space, in a phase space that is not just position and momentum, but it has position, momentum, time, and energy. And that is the expression that you use, and this h is typically not the generator of time like the normal Hamiltonian, but this is actually the generator of proper time. And if you write things like this, you can also have antiparticles in classical mechanics. Things work a lot better. This is essentially how you extend things properly in time. So once you have this, you go and compute the transformation rule for your bases, which I'm not going to do. If you want to see it, you can pause and look at it, or I'm going to put a link to these notes in the description so that you can see how it works. And now I don't understand. Look at that. The arrows are remaining. That's not good. I'm still trying to understand how to use this program, and evidently I don't know how to use it that well. Okay, so the point is that if you go through the transformation, you get the expression of the canonical form and of the symplectic form in coordinate of position and conjugate momentum, not conjugate momentum, of kinetic momentum. And what you see is that if you define your energy, your electromagnetic tensor in the usual way, you find that the part of the symplectic form that has to do with space has actually the force field there. So you could interpret the EM force field as describing how many configurations are there in areas of position and position, which you typically wouldn't have normally if you had position and momentum, but in position and kinetic momentum, what it turns out that is that you actually have a contribution. And so you can kind of understand this as sort of coupling the degrees of freedom, so between a position and the kinetic momentum, and so if there is a force, the degrees of freedom expressed as the position and kinetic momentum are no longer decoupled, they're no longer independent, but they're coupled together. And you can go further and you can write the Poisson bracket, which are the classical version of the commutator, and you can see that the position, the Poisson bracket between position remain the same. What changes is when you do the Poisson bracket between kinetic momentum and kinetic momentum, and you find the EM force field. So the force field is basically, again, in terms of Poisson bracket, is just the Poisson bracket of kinetic momentum and kinetic momentum. So you basically see that these elements, this electromagnetic force fields, comes pretty naturally when you're looking at the geometry of classical mechanics. And then the other thing that you can do is calculate the laws of motion by taking, so again you see this S now, we're doing as we said before, this Hamiltonian constraint is not the generator of time, it's going to be the generator of affine parameter, which in this case is going to be exactly the proper time. And so what you do, you do the commutator with the Hamiltonian, and basically what you get is 1/2 G alpha beta, the kinetic momentum, and therefore what you find is essentially that the what's it called, the velocity is the kinetic momentum divided by the mass, which is the velocity, so it makes sense and it actually works. Then the other thing that you can do is see how the kinetic momentum itself evolves. So again, you just do the Poisson bracket between the kinetic momentum and the Hamiltonian constraint, and you do a bunch of calculation, and what you find at the end, it's essentially that you essentially have an equation, kind of an equation of a geodesic already embedded inside here. So things work out as you would expect if you were trying to write relativistic equations. So okay, so this works. And now what is I think even more interesting to me is redoing this work. Instead of using position and kinetic momentum, write everything in terms of position and velocity. So if we do that, again, you're going to get that the Hamiltonian constraint is just essentially the norm of for velocity, and the norm for velocity is c squared. So this is essentially, the Hamiltonian constraint is just 1/2 mc squared. It's a constant of motion. And again, if you do all your calculation, that again, if you want, you can either pause or look at it. It's nice to see how the symbols move and so on, but I don't think it adds much me saying how these things work. And what is interesting to me instead is that what comes out of this calculation is this. This is the final result. Is that in the sort of position velocity terms, the diagonal term, the metric tensors appear. So the metric tensor can be understood instead of defining the distance and the angle in a position, can be understood as telling you sort of giving you the number of configurations between if you're using position and velocity as degrees of freedom. So it tells you volumes in the space of position and velocity, which is where you would put your distributions of states. And the other thing that is interesting, and again, I don't know what this thing is doing, but okay, as long as you can read there. Okay, what is interesting is now this component here. We have the EM tensor as we had it before, but now we have this other expression here, this G alpha beta, which is the thing that I told you at the beginning, which is simply this kind of anti-symmetrized derivative of the metric tensor, and it's contracted with the velocity. And so looking at this, of course, I know what this thing is. I know what this thing is. what is this thing? Again, it comes out from doing the simple calculation of trying to understand the geometry as expressed in position and velocity, which actually position and velocity are the things that we actually want to use because they're the things that connect to the physics, where conjugate momentum is this weird quantity that it's not really physical. And so it would be interesting to understand what that thing is, and I've been looking at this for like quite a few years now, and I've asked a bunch of people, and nobody seems to have seen this thing. And what I'm doing here is just doing the contravariant components, and what I'm doing then here, I use that to calculate the Poisson brackets. And as you would expect, the Poisson bracket between position and position remains the same, remains 0. The Poisson bracket between position and velocity now becomes the metric tensor divided by m. And the Poisson bracket between velocity and velocity, again, they have their term with EM field, but they also get now this other term with this mysterious pseudo-tensor type thing. And one, again, you can, as before, use the Poisson brackets to get the laws of motion, and you are going to find that the velocity, the change of x alpha in proper time is the for velocity, which is, again, makes sense, it's what you would expect. And then you're able to calculate the velocity, the change, the derivative of the velocity, the acceleration, and you find here, of course, the term that it's given by the force, and you find the other part here, which actually these two things combined become the covariant derivative, and so you have the equation of the geodesic. So what is interesting to me is, let's see, I think it's this line of the expression, because we have kind of a change in, a change of the velocities, where basically I could understand this as a force, and of course it's not a it's not a covariant force in some sense. This is covariant, right? This is a tensor, this is a tensor, this is a vector, so things work out. And what happens here is that we have kind of this part here, which is our tensor here, which kind of would make, which again kind of tell us that this is somewhat of a force in the same way that this is a force. But then we also have this other term here, and what you get is that this term put together, they give you a Christoffel symbol. And that happens because this expression, if you do some math, is actually equivalent to one Christoffel symbol, and this is actually the difference between two Christoffel symbols, and so these two go away and you get only one. And so I still don't understand what this thing is, and one of the first things that I sort of trying to understand is whether this thing is a tensor or not. And if you look at the expression, you're very suspicious that it's not a tensor because it's a derivative of the metric tensor, or it's the difference between two Christoffel symbols. And if you've done general relativity, there's very low chance that these are invariant. In fact, what happens if you take the reference frame of a spinning frame, like the metric tensor of a spinning frame, and you calculate, you do find that the G alpha beta gamma is non-zero, right? So it's not a tensor because this clearly is zero if you are in Cartesian coordinate, in inertial frame in Cartesian coordinate, because everything is a constant, so the derivatives are all zero, so all the elements are zero, and so it can't be a tensor because you have it in one reference frame, everything is zero, but in another frame, not all the elements are zero. But curiously enough, there is this anti-symmetrization, right? So some pieces go away. And so one of the things that I noticed when I do the calculation in the spinning frame is that the centrifugal force remains, like the elements of the centrifugal force are there in the G alpha beta gamma, but again, if I didn't screw up the calculation, the Coriolis force instead cancels out. It's not there. Elements of the Coriolis force are not there in the G alpha beta gamma. And so this would kind of make sense in a way that the G alpha beta gamma get only the conservative parts of the inertial forces and not the non-conservative parts. So maybe that's what's being done. I have no idea. That's just a thought, and if somebody wants to explore it, that could be a way to look at it. Another thing that I did to sort of understand what the thing is that if you do some calculation, you know that the anti-symmetrized covariant derivative on a vector is always equal to the anti-symmetrized standard derivative, partial derivative. And what it turns out is that if you do the sort of the other version with the upper indices of both, what you find is that this G alpha beta appears as a correction of the anti-symmetrized derivative, up derivative, from the sort of the standard one to, so it's the way that you go from the standard derivative to the covariant derivative. And so I would think that it's picking up some geometric information, but again, I don't know what exactly is picking up, and it would be interesting to know. So that's it for this mysterious expression. If you have any hints of what this thing could be, if you have ever seen it somewhere, if you know what the geometrical interpretation of this thing could be, leave a comment below, and thank you again for your attention.